A half-wave diode rectifier circuit is driven by 60 Hz sine wave with a peak value of 11 volts. If our load resistance the circuit drives by is this value and the ripple voltage is this value peak to peak, then what is our average current? So we are going to be looking for something in milliamps as our answer, and we're looking for average current. So we can look at the notes linked below the like button. And the important things to note is that we have a half-wave diode rectifier. So we're going to be looking in the diode notes. We're going to be looking in the half-wave section specifically, so we can just search up half-wave, Control F or Command F, and it'll bring us to one out of 4 of these search results. And this is going to be the search result that we are looking for. So let's jot down everything that we know so far. First, we know that our frequency is equal to 60 Hertz. We know we have a peak value of 11 volts, so our voltage peak is at 11 volts. Our load resistance, so RL, is equal to 6.7 kilo ohms. And then our ripple voltage at the output, which is going to be VR, peak to peak, is 0.42 volts peak to peak. Now don't get this confused with this peak to peak. This is basically just saying, well, we have this peak to peak value and the voltage output is going to be 0.42 from the peak to the peak, so the entire time of it. So that is something we don't want to get confused on. Now if we look at the notes right here, we know we want to find our average current. So let's look at that. We have ID average right here. So let's write this out. We have our ID average, and this is equal to, we have two different ways we can write it. We're going to write it the second way, and that's because we don't have the T's or the delta T. We instead have VP and VR. So we're going to do IL, and then inside of here we have 1 plus the pi times the square root, and then inside of our square root we are going to have 2. We are going to have our VP, and the VP is our peak to peak value, which is 11 volts here. And then this is going to be our VR, which we know to be 0.42. So we're just plugging in values. Again, our VR is going to be this value. Our VP is going to be this value. And then we can just close this parenthesis. Now, we need to find our IL. So let's do that next. Well, if we scroll up, we have an equation for IL right here. IL is just going to be equal to the voltage peak over the load resistance. We could see that from here as well, but it's really apparent in the equation that we have right here. The filter capacitance is chosen such that our RC is much greater than our T, so the normal exponential capacitor discharge appears linear. That has to deal with capacitors. We're not really looking at that information here, but that is also important to understand the capacitance and how that translates to current, because we're taking the derivative for it as well because of the D's, and then we have these deltas. So what we're going to do is just plug in for these values. So we know our VP is 11 volts and our RL is going to be 6.7 kilo ohms, so times 10 to the cubed. Now I'm going to plug this into a calculator like this. Notice how I have everything plugged in except this 10 to the cubed right here. And that's because if we just look at this part down here, just our IL, if we just do this, we are going to get some value, some number, and then we could rewrite our 10 cubed as 10 to the negative cubed. And we know if we have 10 to the negative cube, this is equal to 1 milli. And we want 1 milliamp as our answer. And so that is why I just omitted this. That way we can have a milli in our answer without having to convert it again. And if we do that for our answer, we are going to get approximately 38.97, and this is in milliamps. And that's how we would look at solving this problem. If you have different values or anything like it, we would just follow the same process using the notes that we have right here.